Okay. Let's get started. So today we are going to talk about, I guess, the most important topic of this whole course. That's the Fourier series representation of continuous time periodic signal. This is one of the four Fourier representation or Fourier transforms we are going to talk about in this class. Okay, and so here we start with this handsome picture of Fourier here. Okay, so this is a Fourier for the Fourier transform and the Fourier series. And his full name, Jean-Baptiste Joseph Fourier. And I guess we start with a bit of a history how Fourier come up with the Fourier series, or Fourier's history of trying to get this Fourier series published. Okay, and this is a kind of a sad story. And so as we know, Fourier come up with the idea about Fourier transform and the Fourier series. And the idea is that, as we talk in chapter 1, there are those harmonic series. There are those harmonic functions that are all pure. So there are those sinusoidals that are all sharing the same period, big T here. And the idea of Fourier series is we want to represent any signal with a linear combination of different harmonic functions. Okay, so we can think about we have a higher and higher frequency oscillation, and we add a linear combination of them together. They are still periodic with some period. And Fourier want to represent any function with some linear combination of those harmonic sinusoidals. But when he tried to publish his result, he got a strong objection from Lagrange, which is another famous mathematician. The objection was that, well, if you try to represent this triangle signal, then you see that you have a kind of discontinuity in your slope here, so you have a sharp angle here. But you are adding together all those sinusoidals, and all those sinusoidals has very continuous differentiation. So they are all smooth here. So it should be impossible to add up those smooth function to get a function with sharp edge here. Okay, and so Fourier had trouble to publish his paper. And but as what we learn in today, then we are still going to represent the function with the sharp edges with just those sinusoidals, and we will see that they are both Fourier and Lagrange are kind of correct in their perspective. So we are going to see that when we add an infinite number of those functions, then we can indeed try to approximate this sharp edge here, but there will be some consequences that you need to deal with. Okay, but anyway, so this is a very short introduction of Fourier series. It's invented by Mr. Fourier. And okay, so let's go to straight go to our Fourier series representation of continuous periodic signal. Okay, and so as a reminder, we want to represent any periodic signal with those harmonically related complex exponentials. And so here is a bit of review. So in chapter 1, we say a signal is periodic if it satisfies this condition. So this is a mathematical definition of periodic. It means that you do a tangent with some period big T, then the signal is the same. So x of t equal to x of t plus big T. And then a signal has a fundamental period, which is the smallest positive period big T. Okay? And also there is a fundamental frequency, and it's defined as 2 pi divided by big T. Okay? And so those are periodic review. And then we have those harmonically related complex exponential. Okay? And also there are sinusoidals that are kind of related to those complex exponential. I guess we should say in this way. Okay, so there are two signals that are periodic that we studied in chapter 1. So first is complex exponential with purely imaginary exponents. So we know e to the ij, so e to the j omega naught t. If omega naught is a real value, then j omega naught is imaginary. So e to the j omega naught t we know is periodic with period 2 pi divided by omega naught. And so that also means that its fundamental frequency is omega naught. And also there is a closely related signal that are those sinusoidals. So it's the cosine omega naught t and the sine omega naught t are also periodic with period this big T. And we know they are very related. Say the real part of this e to the j omega naught t is this cosine omega naught t. And because those complex exponential is hard to draw, it's a complex function. So usually we'll draw sine omega naught t or cosine omega naught t to represent this thing. So when we draw this actually sine function, we kind of mean we are drawing this e to the j omega naught t because we know it's oscillating. It's both its imaginary part and the real part is oscillating like a sinusoidal. Okay. Anyway, let's go back to focus. Yeah. Excuse me, it's a bit too low. We are getting echoes. Let me try to fix this volume. Okay, it is okay. So this is a bit better. Okay, and yeah. Anyway, algebraically we will focus on this e to the j omega naught t, and then so they are periodic with period big T, and then we talk about harmonically related complex exponential. So there are a set of functions or signals that's indexed by this k here. Okay? And then the notation here is a bit funny because now we have this big T that's same for AV over psi k. Phi k. Okay. So the notation is a little confusing, but hopefully we know from context. So before this sentence, the big T was the fundamental period for whatever your signal here, and now big T is a period. That's big T is actually not the fundamental period for every psi k. So big T is a common period for every phi k. So every phi k is periodic with the period big T. And the signals are like those. They have form e to the jk omega naught t. And we think about is they are all sharing the fundamental period big T here. Okay, so it's important to have big T here. Okay, big T. So those are signals that all share the fundamental period big T, and they are just oscillating faster and faster. And so for k equal to 1, it has is equal to jk omega naught t, and it's just that its fundamental period is big T, and it's oscillating once in this big T period. And for k equal to 2, then the signal oscillating twice in this big T period, and for k equal to 3, oscillating 3 times, etc. Okay, so the fundamental period for psi k is getting smaller and smaller when k is larger, and its frequency is higher and higher. So its frequency is k omega naught. Okay, and yeah, so as we say here, they have fundamental period big T divided by k, and they are all periodic with period t. So p is a common period for all those signals. Okay, and yeah, then we write down the definition of our Fourier series. So Fourier series representation for periodic signal is just a linear combination of those psi k. So it's a linear combination of those harmonically related complex exponentials. So yeah, so you see the phi k, the phi k's are here, e to the jk omega naught t, and you have a linear combination length of them, so you sum over those k, and you just give different coefficients ak for each psi k. Okay, so yeah, it's pretty straightforward. So this signal, we write down this Fourier series is just a linear combination of those psi k. And it's pretty clear that this signal, for whatever ak you pick, so ak will be just whatever complex number you like, And for whatever set of AK you pick, this thing will be periodic with period big T. Because every one of them is periodic with period big T, and you add them together, it's still periodic with period big T. Okay, so that's I guess one part. So there will be two equations for this Fourier series representation, and this is the first one. This is you write down your AK, then you can get the signal X of T. Okay, and yeah, you write down AK, you write down this series AK, and then you will represent the X of T that's periodic with period big T. So this is the equation that says that you write down the set of AK, then you'll get some X of T. Okay. And yeah, so this is that, and there are different forms you can write on the right hand side. So it's just saying omega naught is also just 2 pi divided by big T. If you want to be explicit about the signal is periodic with period big T. Okay, and a few more notations here. So. So for different case, you will correspond to different terms on those 5K. And for k equals 0 is it be special. You see that when k equals 0, this e to the jk omega naught t is just 1. So that term is just a constant. Okay, so it's just a0. And for k equals to plus 1 and minus 1, that's the slowest oscillating one without being a constant. And they have the fundamental frequency omega naught, and those two are called the fundamental component or first harmonic component. And similarly, if k equal to n or minus n, it's called the nth harmonic component. Okay, and yeah, so this is a Fourier series representation of a periodic signal X of T. Okay, so yeah, so X of T you think is summation, a linear combination of those 5K, and they write down in a more complex expression, then is summation K, aka 5K. Okay, and yeah, first harmonic, fundamental, or second harmonic, etc. Okay, and let's see an example. Okay, and the example with omega naught equal to 2 pi and big T equal to 1. Okay, and our X of T, here we don't have too much component. We only have 6 component with k from minus, I guess actually 7, from k from minus 3 to 3. And as we said, we can list our A, so our A from A minus 3 to A plus 3, and we can get some X of T. Okay. And so we have A0 equal to 1, A plus minus 1 equal to 1 over 4, A plus minus 2 equal to 1 over 2, and A plus 3 minus 3 equal to 1 over 3. Okay, and and then we can write our X of T, and we have pick our AK with some special relation. So our X of T is actually a real function. Okay, so because you see there is some symmetry between those plus minus k. So X of T is this A0 times e to the J0 2 pi t. So when k equals 0, as we say, it's a constant term. So this A0 term just become 1 for your X of T. So it's a constant 1. And for other terms, we have for this plus and minus 1, then we have 1 over 4 of this e to the plus 1 to omega t, and e to the minus 1 j omega t. Sorry, e to the plus 1 j omega j 2 pi t, and e to the minus 1 j 2 pi t. And those combined together, they become 2 cosine 2 pi t. And similarly, for k equal to plus minus 2, you have this e to the j plus minus 4 pi t term, and they combine together to cosine 4 pi t. And for those two terms, you have this cosine 6 pi t term with coefficient those 1 over 3 times 2. Okay, and let's see this in a picture to see what's happening. So we have those 1, 2, 3, 4 components that correspond to 1 and cosine 2 pi t, cosine 4 pi t, and cosine 6 pi t. And so we have 1 here, and so this is x0, and we have cosine, sorry, it's actually here. We have x0 here is 1, is a constant function, and then we have the first harmonic component, that's x1, and it's oscillating with lowest frequency possible. And so you have one period being this one oscillation here, and it's cosine 2 pi t. So we have a big T here, big T actually equal to 1 here. And then we have x2, that's cosine 4 pi t, so it's oscillating twice as fast as x1. And you see that in this 1t period, it's oscillating twice. It goes up, down, and up, down. And then we have x3 that equal to 2 over 3 cosine 6 pi t, cosine 6 pi t. And so you see that in one period, so it's oscillating 3 times. So one period should be 1, 2, 3. Okay. So this is one period, and it will oscillating 3 times. Correspond to the components for k equal to plus minus 3. Okay. And then we see that our XOT is adding all those four together, and we try to have the adding them one by one. So it starts with x0 equal to 1, then you get add x1 up here, and so it's constant, so you just shift x1 up to this oscillation like this, and then you add x2, then you see that you have this slower oscillation adding with this faster oscillation, and so you see that in one period it has the different peaks. So you have those peaks with the slower oscillation, and the different peak with the faster oscillation, and then finally you add this thing with your x3, which is oscillating 3 times in one period, and you see you have a more complicated signal in this one period. Okay, and yeah, so this is the idea of Fourier series representation. You can add up those harmonically related complex exponential and get some signal. And I guess here the only thing we know is that you add those harmonically related complex exponential, and they are all periodic with period big T, and you see that the resulting function is still periodic with period big T. Okay, any questions so far? Not? Okay. And yeah, I guess here we haven't derived anything. The derivation is harder later. Okay, and I guess here we start with some derivation. So Fourier series representation, we actually okay, and as we said, so you have any AK, then you can get the XK. Okay, so AK can be any complex number. Instead of complex number, like it's infinite. Yeah, is a set of arbitrary complex number for those AK. And by your x of t is a real signal, then there is some special relationship for AK that they need to satisfy. Okay, and yeah, so this is a relation that's pretty useful because I guess a lot of real life signal have real value. Say if x of t is your current or voltage, and usually you think it's a real value. Okay, and here the derivation actually we use something that we haven't proved yet. So we need to use the property that so we have the property that if you have a fixed x of t, actually those AK will also be fixed set. Okay, so AK is a unique set for every x of t that we'll see later today. Okay. And anyway, so if your x is real, then for a real signal, then the signal is equal to its complex conjugate, and then we can see what happens to when you complex conjugate everything here. So we just complex conjugate everything, and the AK become complex conjugate of AK, so AK star, and this e to a jk omega naught t becomes its complex conjugate, so you get a minus sign up here. Okay. And then you try to make this look like this. So you do a change of variable, you change k to minus k. So change k to minus k, then summation k is still minus infinity to plus infinity, because this plus infinity become minus infinity, and this minus infinity become plus infinity. And by changing k to minus k, so this minus sign disappear. This is what we want. So you still got e to a jk omega naught t here, just like this e to a jk omega naught t. And another case here, so this k become minus k, so you have a star minus k here. And as we can, we said AK is actually a unique set, So we will have that a to the star minus k should equal to a to the minus k. So this is what we get, and yeah, so this is what this formula is what we get. So ak equal to a star minus k if x of t is real. This is the first derivation we get for Fourier series representation. Okay, and I guess another form of this is you can put the minus sign on the other side, then you get a to the minus a of a sub minus k equal to a star sub k. Okay. Okay, so this is what needs to happen for real signal, and let's see. So for this example, we see that it is satisfied because so I guess the first one is a0. So for a0, then minus 0 is still 0, so we just get a star of 0 equal to a0, so a0 needs to be real. And you see that for this real signal, so a0 is indeed real, and then ak should be the complex conjugate of a minus k. Okay, and so we see that all those ak is the complex conjugate of a minus k, because both ak and ak are real. Both ak and a minus k are real, and yeah, and they are equal to each other. Okay, so we see that this example check out, and yeah, so that's the result. This is a nice relationship to remember. I guess it's nice to remember because you can check whether your AK is correct. So if you know your signal is real, then you can have this relationship. So I guess it's useful in two ways. So first is when you calculate AK and then you know your signal is real, then you can use this relationship to check whether your as a sanity check to see whether your calculation is correct, because it must be satisfied. And another use of this is you can be lazy when do this calculation, because you can only calculate the positive k. Then if you know x of t is real, then you calculate this for positive k, then you already know the negative k, because you know the negative k is just positive k with complex conjugate. And anyway, so we have this relationship, and with this relationship, then you can express x of t in other way. So we write down this summation. As we say, we know the positive k, then we already know the negative k. Okay, so we write this x of t as summation of positive k and the negative k. So we have k from 1 to infinity, and plus k and minus k. And then we know the negative k1 is just positive k with complex conjugate. And then we can combine those two to be, then we see that this is the complex conjugate of this. And so we add up the complex conjugate of two things, then it's just the real part, twice the real part. Okay? So yeah, we see that indeed you have this thing, then your x of t is real. Okay, and I guess here we finish to prove that this is if only if relationship. So x of t is real if only if ak equal to a star minus k, or a minus k star. Okay, and then we can have more form to represent our real signal. Okay, and because kind of we want to represent our real signal with real functions. So you can do away with this complex exponential. So you can actually just represent your real signal with cosine and sine. And yeah, and so you write so you use our Euler relationship. So you write your AK as so first you write with polar form AK e to the j c dot k, and so this is just and with this big AK real and the theta k real, then this becomes just cosine omega big AK and the cosine omega t plus theta k. And yeah, so basically you, instead of parameterizing your x of t with those small ak with complex value, you are parameterizing with this big AK and theta k, both real value. And you see that this expression is immediately real, because you have cosine omega k omega t plus theta k. This is a real function. And then you can also do some trigonometry to break this cosine omega t plus theta k into cosine and sine, and rewrite your big AK and theta k into another coefficient that's bk and ck, and so instead of AK and cosine k omega t plus theta k, you can also write your real signal as bk cosine k omega t minus ck sine k omega t. Okay, so you can also write as a linear combination of sine and cosine with different coefficient bk and ck here. And and ck and bk are both real. Okay, so that's important here. So yeah, and this is immediately real. So bk and ck are both real. And so yeah, so that's a nice expression for that's a nice expression for real valued signal. So real value periodic signal, you can also write this periodic, it's a Fourier series as this AK cosine plus theta cosine or BK cosine plus CK sine. Okay, and that's for real signal. And I guess let's go back to the most important part of today's lecture. Okay, so that's the other way of the Fourier series representation. So we say that we add up those Fourier series, we can get a periodic signal. And but there is something very interesting happening is actually for every periodic signal with period big T, we can write it in terms of a Fourier series. And we are going to derive in our next 20 minutes how you find the AK corresponding to your XK. So before, so this expression told you how to find the x of t from your AK. You just sum over those functions. And then we are going to see that how you, when you are given a periodic signal x of t, how you find those AK. Okay. So yeah, we want to express any periodic signal with period big T with this Fourier series representation. And so basically we want to find the AK for every periodic signal x of t. Yeah. And so let's start with this. And so the insight of this is that we think so those psi k, so those e to a jk omega t, this is kind of like a linear. We view this summation kind of like summing together vectors. Okay. And we actually think those functions are kind of orthogonal to each other. So the idea is, I think the high-level idea is, hopefully you still remember linear algebra. So if you have some vector as a linear combination of different basis vectors, then you can find the coefficients here by doing the inner product of your vector with your basis vectors. Okay. And so the doing inner product thing we are doing here is we are going to multiply our signal with so now we are trying to find some an, so a for some number n, and what we are going to do is we'll multiply with those so we are trying to do inner product here. So inner product is like multiplying together and summing over all dimension. And so what we are doing here is we multiplying together and we integrate through one period. And but it's a bit different than the real value. But here everything complex value. So when you do this multiplication together, instead of just multiplying e to a jn omega t, you multiply with e to a minus jn omega t. So you have a h1 minus sign because this is complex value. So you multiply with a complex conjugate of this e to a jn omega t, and so you multiply both sides of this equation with this e to a minus jn omega t, and then you do integration with one period big T. Okay, and so something very good should happen, but let's first see what is our expression here. So you multiply both sides, so this equation, both sides you multiply with e to a minus jn omega t, and then you integrate with one period big T. And so on the left hand side we just leave it as this. So it's some expression you can calculate, is some integration of some function. So it's your x of t, when you should know your x of t, and this is some fixed function. And you can integrate this, you will get some value. And on the right hand side, this will be some expression related to an. Okay, I guess here we should all highlight those n. Okay, so n is the important number here. Okay, so we are trying to find the an. So we should try to highlight those n. Okay. And anyway, so on the right hand side is where we do calculation. Okay, so we do integration here, and you have the summation k and the e to the jk omega naught t, e to the minus j omega naught t. And so first we combine those two exponential. This is just e to the j k minus n omega naught t. And then we see that this integration is linear, so you can switch the order of the integration and the summation. Okay, so you can switch the order of integration and summation, and the integration is on t, and those ak is not a function of t. For t, ak is just some constant, so you can pull all those ak out of integration. So you have the summation k ak, and this integration of this function e to the jk minus n omega naught t. Okay, and so now the interesting thing is this integration. This integration into a jk minus n omega naught t, and we find out that it's like a delta function. So when k not equal to n, this is 0, and when k equal to n, this is t. And I guess let's start with the easier case. So when k equal to n, then this is the integration of 1. Obviously, this is e to the 0 equal to 1. And integration of 1, then over a period big T, then it is just big T. Okay, so in terms of for a picture, it looks like this. You integrate one period with height 1, and this is big T. And when k not equal to n, then we have a very interesting cancellation. Okay, so basically when k not equal to 1, then you have this harmonic exponential. Okay, so it's an oscillating function, and so you see this is just phi of this thing is basically phi sub k minus n, right? So this is complex exponential with a period big T. Okay, so here we have an example of k minus n equal to 1. Then we know the function kind of look like this is oscillating with a period big T. And you integrate it through one period, then this thing is just 0. And you can check that with actual algebraic calculation here. Okay, so you do integration, this is the exponential function, and so you get 1 over the coefficient here, so j k minus n omega naught, and then you have this e to a j k minus n omega naught t with the upper and lower with the 0 and the big T. But for this 0, then this is just 1. And for big T here, then you know big T omega naught will be 2 pi. So this is e to a j 2 pi times some integer. And this is also 1. So the upper bound is 1 and the lower bound is 1. You subtract them, it becomes 0. Okay. And yeah, so you see you have this cancellation here happening when k not equal to n. When k not equal to n, you are integrating over basically this harmonic complex exponential, and the integration should be 0. So for k minus n equal to 1, you integrate over one period, it's 0. And for k minus n equal to 2, you integrate over 2 periods, it's still 0, etc. Okay, and so we combine those two equations to this equation. You see the integration into a j k minus n omega naught t dt equal to t when k big T when k equal to n, and 0 when k not equal to n. Okay. And then you put it back to this right hand side equation. Then you see that when you sum over k here, so you have fixed n here, and you sum over k, and you see that for every k not equal to n, you got 0, so you don't need to think about k not equal to n. And when k equal to n, you got a big T here, and this is an here. So the right hand side is tan, and that's how we get our an. Okay, so you divide big T on both sides, and then finally we got the result of our the result 1. So we see that an equal to 1 over big T integration 0 to big T x of t and e to the minus jn omega naught t dt. Okay, and so this is how you calculate an for every periodic signal with period big T. And also because we have explicit excuse me, we have an explicit expression here, so you will see that when you fix x of t, the ak is a unique set as we claimed before, because you can directly calculate every ak or an with this formula. Okay, and yeah, so that's the Fourier series, two of the Fourier series equation that we have here. So first is the synthesis equation. That's how we go from the set of ak to x of t. So we have a set of ak, then we can get a periodic signal with a period big T x of t. And then we have a periodic signal with a period big T. We can also calculate the ak with the derivation result get. Okay? And yeah, we do a bit of change variable. Here we will say an, here we will say an equal to this integration with jn here, and just change n to k, then you get our equation here. So a sub k will equal to this 1 over t, integration over a period big T, x of t to the minus jk omega naught t dt. And then you can also write your omega naught as 2 pi over big T. And here we do a bit of generalization, because in a derivation we were doing an integration from 0 to big T, but obviously you see that these two equations doesn't need to start from 0 to big T. You can start, say, from big T to big 2T, to big T to 2 big T, then those two equations still hold. You only need to integrate through one period. Okay, and to express that, we have this H1 notation integration big T here. Means that it's integration over one period. So it's from some arbitrary t0 to t0 plus big T. Okay, and t0 can be arbitrary value, and our derivation was setting t0 as 0. Okay, and yeah, so this is our Fourier series representation, and it's two set of it's a set of two equations that translate between our periodic signal with period big T x of t with those set of Fourier coefficients ak. And yeah, as we just said, the AKs are called the Fourier series coefficients, or spatial coefficient over x of t. Okay. And H1m, so A0 is called DC, or constant component over x of t, because A0, and you can calculate A0 as this 1 over t integration of x of t. So this is basically the average of x of t. And it's a constant component because it represents the constant signal. For in terms of this A0 e to a J0 omega t is just A0. Okay, and that's almost finished everything. I guess let's talk a little bit about math, so we can make our our argument of this linear combination, this linear algebra a little more rigorous. Is you can define inner product between periodic functions. So you can define a inner product between periodic functions as inner product between f of t and g of t as is integration over big T, the complex conjugate of f of t and g of t. And then you can see, you can show yourself that this relationship satisfy all the property you want to have on inner product, and also this will define the norm on your functions. So norm of a function will be inner product with yourself, and yeah, then it's an integration of the absolute value square of your function over one period. And yeah, so if you will check one thing good about this inner product is you can define a norm here, and the norm is a positive number. Okay, and I guess finally we have quite a few bits of slide. And anyway, so here some supplement material. This will not be in our test, but something nice to know for your application of a Fourier series. So basically the Fourier series representation. So we have two very specific formula here, but unfortunately there are different different notations of Fourier series on different book and application. So yeah, so people just like to have different conventions for Fourier series. Okay, and so for example, sometimes instead of those omega, so those angular frequency, you would like to have those frequency that's 1/, your period. Okay, so like how many rotation per period you have, and then you will get HR 2 pi here. So you have 2 pi f, 2 pi f here, and also sometimes people would like to have a different. Would like to have more symmetry between your synthesis equation and the analysis equation. So instead of having 1 here and 1/t here, you will have 1/big T on your x of t, square root of 1/t and the square root of 1/t. And you can check out those two equations still are still consistent. So you transform ak to xt like this, then you can transform xt to back to ak like this. Okay. So yeah, so those are just different notations you might see in different books. So yeah, be careful when you read up the Fourier series transform on different sources because they have different conventions. So make sure about the conventions you are dealing with first. And anyway, but you should remember those conventions for our text for this course because this is the definition of Fourier series representation we use in this course. Okay, and I guess let's see. Okay, so for 5 minutes, we will see a few examples of our Fourier series representation formula. Okay, and yeah. So we start with our very easy example. So x of t is a real signal sine omega naught t. And yeah, so we want to determine the Fourier series coefficient of this thing. And then we can write down those integration, but this is so simple we don't even need to write down the integration. So because we can just break this into the complex exponential by this reverse order formula. Okay, and yeah, so we just have sine omega naught t equal to 1/2j e to the j omega t minus 1/2j e to the minus j omega t. Okay, and I guess here the hard part about this is you need to determine what's the what's the fundamental period for this signal. But we also know the sine signal very well, so we know the fundamental period is 2 pi over omega naught, and omega naught is your fundamental frequency. So those two signals is just those two complex exponential is just correspond to complex exponential with k equal to 1 and k equal to minus 1. Okay, and yeah, so just by eyeballing this equation, you see that your sine omega t has a1 equal to this 1/2j and a minus 1 equal to minus 1/2j. And then you have ak equal to 0 for all other k. Okay, so that's one example of our Fourier series representation. So you have those periodic signal, and you see that you can calculate this ak with this result. So a1 equal to 1/2j, a minus 1 equal to minus 1/2j. And we have a similar example that's more complicated. So, but also we still don't need to do integration. So we have 1 plus this sine omega t plus 2 cosine omega t plus cosine 2 omega t plus pi over 4. And so similarly, we still don't do integration. We only break sine and cosine into the linear combination of complex exponential. So sine you break into 1/2j of e to the plus and e to the minus e to the minus, and the cosine you have cosine omega t break into e to the j omega t, e to the minus j omega t, and then we have this cosine 2 omega t plus pi over 4. You still break into e to the j 2 omega t plus pi over 4, e to the minus j omega t, e to the minus j 2 omega t plus pi over 4. And so how you deal with this h pi over 4 is you see that you break those break this exponential to the e to the j to omega t part and the e to the j pi over 4 part, or e to the minus j pi over 4 part. And this is just another constant, so you can multiply it with your 1 over 2 to become your AK. Okay, so you see that this thing has a whole bunch of different AK. So this one term is the DC term, it corresponds to A0, it's just a constant. And you can read your A1. So A1 are the coefficient related to e to the j omega t. So it's from this so it's from this 1 over 2j plus 1 here. Okay, so it's 1, A1 is 1 plus 1 over 2j. And similarly, you A minus 1, you get from this minus 1 over 2j plus this 1 here. And then you have A2 equal to this thing here, and A minus 2 equal to this thing here. Okay, and we can plot the beta of our A. So we have, so we list our A here, and we can plot our AK as a function of K on a line. And by AK are complex value, so we plot it with polar coordinates, so we have the opposite value of AK here and the angle of AK here. And you see, so those are results. Opposite value with those things. So opposite value is non-zero only if when AK is between minus 2 and 2. And also angle is non-zero between those minus 2 to 2. Okay. And I think we are exactly on time. So next time we will start to talk about more examples. So we have a more interesting example next time. We are going to see how this black wave get break into Fourier series. And we will talk about convergence of Fourier series and properties of Fourier series. Okay, so see you next Monday.
上礼拜交纸本作业的可以